For decades, humanity has chased the ultimate energy source, nuclear fusion. Not the fission used in existing nuclear power plants, which splits heavy atoms and produces radioactive waste, but fusion, the process that powers the sun and the stars, which merges light atoms, isotopes of hydrogen, to release vast, clean energy. The promise is simple and revolutionary: energy that is virtually infinite, emission-free, and inherently safe. This dream of mastering the sun on Earth led to the conception of the ITER project, International Thermonuclear Experimental Reactor, an unprecedented global collaboration. Launched in the 1980s, ITER was initially conceived as a joint effort between the Soviet Union, the United States, Europe, and Japan. Its core purpose was to prove the scientific and technological feasibility of fusion power for commercial use. The idea was to build a massive device called a tokamak, designed to confine superheated plasma, a gas so hot it breaks down into ions and electrons at temperatures exceeding 150 million degrees Celsius, 10 times hotter than the core of the sun. This intense heat, contained by powerful superconducting magnets, would force the hydrogen nuclei to fuse, creating a net energy gain, more energy produced than consumed to start the reaction. The ambition was noble, aimed at solving the planet's long-term energy crisis. The initial optimistic cost estimate for this groundbreaking scientific endeavor was relatively modest, approximately $5 billion, with an operational date set before the turn of the millennium. The vision was political as well as scientific. It was a post-Cold War handshake, a promise that nations could cooperate on the grandest scale to secure humanity's future. But the scale of the scientific complexity, coupled with the political entanglement of 7 international partners, the EU, US, China, India, Japan, South Korea, and Russia, turned this noble endeavor into a financial and logistical monster, proving that science governed by consensus can be the most expensive experiment of all. The ITER project quickly became a case study in budgetary oblivion. The initial $5 billion estimate evaporated under the weight of political delays, bureaucratic red tape, and the relentless escalation of engineering specifications. Unlike a fission plant, where components are relatively standard, every single part of the ITER tokamak is custom-made, requiring extreme precision and unprecedented materials science. As the years turned into decades, the cost estimates grew not by increments, but by orders of magnitude. By the 2010s, the official cost projection had quadrupled, then quintupled. Today, the total estimated cost for the construction, assembly, and operation of ITER over its projected lifespan is widely estimated to be north of $65 billion. This makes ITER one of the most expensive single scientific projects in human history, easily surpassing the Large Hadron Collider, LHC. The project became a financial black hole, constantly consuming funds from its 7 partners, none of whom could afford to quit due to the immense political capital already invested. This budget creep was not primarily due to fraud, but to the complexity of collaboration and governance. Because the project is funded by multiple governments, contributions are often made in kind, meaning countries supply components instead of cash. While this sounds efficient, it led to logistical chaos. Parts built in China had to fit perfectly with parts built in South Korea and the European Union, requiring millions of hours spent negotiating specifications, adjusting measurements, and managing supply chain failures. These coordination failures compounded the engineering challenges, leading to manufacturing delays, redesigns, and the continuous ballooning of costs. The ITER project proved that when money is not the primary mechanism of control, efficiency is the first casualty, turning a scientific collaboration into a fiscal catastrophe. The heart of the ITER blunder lies in the sheer engineering impossibility of its central component, the tokamak. Designing a machine that can contain plasma at temperatures 10 times hotter than the sun is a physical challenge of unimaginable complexity, pushing the limits of materials, science, cryogenics, and electromagnetism. The machine's vacuum vessel alone is a labyrinth of custom-welded steel sections that must be perfectly aligned, creating an internal environment of ultra-low pressure while withstanding immense thermal stress. Two components highlight the monumental difficulty and the ensuing delays. First, the superconducting magnets. ITER requires the largest and most powerful magnets ever built to contain the superheated plasma. These magnets must be cooled to near absolute zero, while operating mere feet away from plasma that is millions of degrees hot. Manufacturing these massive magnets with the required precision took years longer than anticipated, often failing quality assurance tests. Second, the remote handling systems. Because the internal components of the tokamak become irradiated, all maintenance, repair, and replacement must be done by highly complex robotic systems operating remotely. Developing these specialized robots to perform delicate tasks within the cramped, hostile environment added years of delay and billions in R&D costs. These unprecedented technical challenges meant that the initial design specifications were constantly revised. The constant need for custom solutions and ultra-precise manufacturing led to an explosion in delays. The original operating date of the early 2000s slipped to 2018, then 2025, and now the critical first plasma date is tentatively scheduled for 2035, more than 3 decades after the initial goal. The massive scale of the engineering has become a self-fulfilling prophecy of delay. Every small technical difficulty requires multinational negotiation and months of redesign, ensuring that the completion date is always receding into the future. The ITER project represents the ultimate scientific billion-dollar blunder, a spectacular effort whose success is constantly undermined by its own political weight and financial cost. The project has birthed the famous joke that fusion energy is always 20 years away, a phrase that perfectly encapsulates ITER's relationship with the public and its funders. The relentless budget creep from $5 billion to over $65 billion means that the initial cost-benefit analysis has been completely obliterated. The ultimate irony is that by being so slow and expensive, ITER has inadvertently incentivized smaller private companies to accelerate their own cheaper fusion research, potentially making ITER's design obsolete before it even achieves full operation. The greatest cost of ITER is the opportunity cost. The tens of billions spent on this single monolithic project could have funded thousands of smaller, agile research projects globally, potentially leading to faster breakthroughs in less conventional fusion approaches. Instead, political commitment to this one massive design has monopolized global fusion funding for decades. ITER is now a symbol of political commitment, overriding rational science management. No single partner can afford to pull out without losing face and writing off decades of contributions. They are locked into the sunk cost fallacy on a geopolitical scale. The project will eventually be completed because the political desire to prove that we did it outweighs the financial absurdity of the investment. When ITER finally achieves its goals, it will be a monumental scientific victory, but it will stand as a simultaneous monument to bureaucratic failure, cost mismanagement, and the paradox of ambition. ITER is a $65 billion question. Will mastering the sun on Earth be worth the financial darkness it created in the process? Don't miss the next blunder. Drop a comment below with the next disaster we should investigate, and hit subscribe so you don't miss a single catastrophic failure. Until then, thank you for exploring with us.